n, which is your ball of actions. Before the perturbation, your variable, your action variable is constant, and the weak form of Arnold conjecture says that you could travel a distance of order of 1, and a strong form of Arnold conjecture says that if you give two open sets, u and u prime, then there exists an orbit which connects them. The word original, I'm not sure. I mean, I've seen it mentioned in Arnold Kozlov-Neistat book. I've seen it mentioned in the paper which Abed showed me. Do you remember the reference? So there are maybe 5 different sources. I mean, if you say that it goes a distance of order of 1, it's natural to say, okay, if it goes distance of order of 1, then. Right. 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 Epsilon. Right. Right. Yes. You first fix u's, and then you choose, and then choose generic H1. Yes, for all epsilon in the range. I'll give a precise statement. Yeah, for any for any epsilon in 0 epsilon 0, n is at least 2. It's time periodic, but yes, you're right. Yes. No. Epsilon is small, but uniformly small. So epsilon is a small parameter. Time goes to infinity. Yeah, because maximal speed is of order of epsilon. So here's the first main result. So all the time H0 is convex, and it's an example. It works for any convex H0. So H0 of P is equal to, the basic example is when H0 is just a kinetic energy, P squared over 2. So the first main result, it says that for any n which is at least 2, okay, at least 2, the weak form of Arnold diffusion holds. And let me give you a precise statement. So this is a theorem 1 from a preprint with 3 authors. It's available on arXiv. It says that for a generic epsilon, for a generic H1, for a generic H1, and I'll give it a more precise description. It should be CR, and my memory is that R is at least 4. I think it's at least 4, but not C0, no. Huh? Oh, Bn. The result will be in B2, but they're in Bn. So for generic H1 and CR, R is at least 4, and epsilon small enough, epsilon small, there exists an orbit, theta epsilon, P epsilon of T, such that P epsilon of 0 minus P epsilon of T is bounded by L of H1, which is strictly positive, and this is independent of epsilon, so L is computable, and independent of epsilon. Independent of epsilon. So what this theorem says, this theorem says that if you give me a perturbation H1, I will do a certain procedure, and after I'll do a certain procedure, I could tell you by how much the orbit could go. And remember, it's uniform in epsilon. So take epsilon as small as you like, and for an arbitrary small epsilon, you have an increment of at least a fixed size. And I'll draw some pictures, but aside of various technical improvements, the key words I believe here is crumpled, normally hyperbolic, invariant cylinders. And I will draw a picture later. And let me formulate the second result. So the second result is you choose n equal to 2, and for n equal to 2, you say that the strong form of Arnold diffusion holds. And let me make a precise statement. So theorem 2, it's a content of the preprints 1 and 2. And what it says that for any pair of open sets in B2 and a generic H1, there exists an orbit theta epsilon p epsilon of t such that p epsilon of 0 belongs to u, and p epsilon of tau epsilon belongs to u prime. So in a closely related form, this result was announced by John Mather 10 years ago. Yeah, and there are notes where some parts of the proof are written. I want to emphasize that our approach is different, and well, we have maybe 2/3 of the discussion which does not appear in the approach of John Mather. So I'll it's cusp residual, but I don't like the word. So you take an open-ended set on the unit sphere, then you remove you remove the cones, and you take open-endeds in the complement. Well, it's again, it's actually in this case R is at least 7, but it's you could do finitely smooth Nekharoshev as Abed did, but usually Nekharoshev is for analytic Hamiltonians, and for analytic Hamiltonians we don't want to make any claims. This is everything is finitely smooth. Right, but then sometimes you want to make a perturbation, and if you are doing an analytic perturbation, it's as if you are handcuffed.
No, I just mean sort of the smaller the R, the better.
Right, and we cannot go below 7. We want to say that generic, at least 7. You cannot go below. Yeah. So there is a KM part which says that you cannot go below. Well, maybe you can with a different method, but okay. Oops. Yes. No. That's the way it's written. H1 does depend on u and u prime, but how to? Okay. So you need to say stop. Yes, yes, yes. It's it's so to tell you the truth. Yeah, to tell you the truth is right. To tell you the truth, it's 2 weeks ago I discussed this with Polterovich, and we suspect that there is a counterexample. You start with something which is CR, you perturb at C0 small, and there are no orbits which travel from one place to another. Mhm. 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 Right. So I think the key point is that when you make smooth perturbation, you have all the KM tori which prevent you from doing diffusion. But if you do C0 perturbation, all of this structure is destroyed.
I think the question is not C0 versus smooth. The question which metric you take.
So CR metric. You want CR dense property because mhm. Right. I think there is an example of Herman where he starts with something with an integrable twist map, and he does even C3 perturbation, and everything is destroyed, and he builds an orbit which goes from up to down, from down to up. And I guess the point is that there are some structures which get destroyed under small, say, C1 or C0 perturbations. And these are the structures which, if you make small CR perturbations, these are the structures like KM tori, which don't let you diffuse. And if you make a very rough perturbation, which is C0 or C1 or C2, then you could destroy all those structures, and the construction of those orbits becomes a lot easier. Answer you to your question, it becomes a lot easier if you don't allow very regular perturbations, because a lot of KM tori disappear. And the KM tori are those which don't let you do it.
Let's say the perturbation are infinity.
Right. Right, but it's C0 small, but C3 large. And if it's C, right, so the question is that you want to study CR neighborhood of integrables. CR. Mhm. Yes, yes. Well, it's kind of exchanging. It kind of exchanging the limits. It kind of exchanging the limits. You might take epsilon perturbation, and you could diffuse epsilon to the minus 100 time. You see? So perturbation is size epsilon, but the time of diffusion is huge. So if you yeah. Mhm. Right.
So what was Herman's result? You said something about
For twist maps, I think it's either C1 or C2 perturbation where he destroys all the invariant curves with a single perturbation.
yes, for C1, I think C2 minus epsilon
C2,
perturbation.
yeah,
Starting with an integrable thing.
right.
But if you start with something that's not integrable,
Yeah, but if you start with something,
even with C1 perturbation, you doesn't know how to destroy it.
Right, but I'm saying that if you are in the framework of Arnold diffusion, and if you allow to do C2 minus epsilon perturbation, you will get diffusion even for twist maps, right? Even for twist maps. So it's KM structure which prevents you from doing this. I think Herman did C2 minus epsilon and Takens did C1. Yeah. No, there exists a perturbation which smashes all the invariant curves and you could travel. Right, so let me tell you the keys here. So here there are, so he construct flower cylinders with kissing property. And they will have a shape of a flower. Flower is a plant. Okay, so let's see. Now I erase here. So now I would like to give Arnold's example, and at least draw some pictures which of two-dimensional manifolds in four-dimensional space, and try to connect it to the whole story. So let me start with explicit Hamiltonian, which was how the thing have started. So this is a Hamiltonian which has two components which are completely integrable. So you have this is a cylinder. So okay, let me finish. So the picture which you have before the perturbation is that this is your QP picture, and this is your phi I picture, and I want to write down equations of motion so that you will see some invariant manifold. So Q dot is equal to P dot is equal to epsilon sine Q. So let me call this one H1. And I dot is equal to cosine Q minus 1 times H1. No, that's not. Yeah, times derivative of H1. And phi dot is equal to I, and now I need to put epsilon somewhere. Derivative is no. I guess I don't. There is an epsilon here. So I guess I don't know if it's visible or not, but if you look at the following set, P equal to Q equal to 0, then this is actually an invariant set. And I really want you to have in mind these pictures that you are in four-dimensional space, and in four-dimensional space there is an invariant two-dimensional cylinder. And so basically if you plug P equal to Q equal to 0, then P dot equal to Q dot equal to 0 is preserved. So this will be invariant. And it's not only invariant, there will be, what is also be important for my story is that you have stable direction along which orbits come in, and you have unstable direction along which orbits come out. And there has been a lot of work in studying Arnold example when you are just doing a generic perturbation. And if you do generic perturbations, then the nice thing is that actually this cylinder, it gets a little bit deformed, but it doesn't get destroyed. And there is a series of papers. There is a paper by Bernard. There is a paper by Chen Yan using variational methods. There is a paper of Treshov. There is a paper of Delayava, Delshams, and Sierra. Basic idea is that if you could keep two-dimensional cylinder invariant in four-dimensional space, then I'm oversimplifying the story, but it's a lot easier to diffuse along a two-dimensional object because you have a much simpler structure to keep track of. And this is so-called a priori unstable. And the naive picture, it would be nice if you have the following naive picture in mind. Sometimes if in four-dimensional space you have two-dimensional invariant cylinders, then using either geometric methods or variational methods, you could diffuse along this cylinder. And notice that the vertical component of the cylinder is I, and I is your action. So for epsilon equal to 0, I dot is 0. So if you manage to diffuse by a magnitude of order of 1, then you have Arnold diffusion. Okay, so if I of t minus I of 0 is O capital of 1, then it gives you Arnold diffusion. Huh? Yeah, so basically it is still hyperbolic, and actually for the actual arguments, sometimes you want to stay on a cylinder and sometimes you want to travel outside and come back at a different place. But it is normally hyperbolic, right? So it still has one direction along which you are contracting, another direction along which you are expanding, and this is what makes this a lot of machinery work. And now let me look at the model problem, and what I want to do, I want to show you some relation with Arnold's example. So model example, it already has most of the difficulties, all of the difficulties you have in general case, but at least some formulas will look more simple. So let me start with the Hamiltonian, which is p1 square over 2 plus p2 square over 2. So n is equal to 2. Let me make an attempt to prove either one of this theorem or two of these theorems. So usually the diffusion is done along resonances. And what is a resonance? So let me give you an example of a resonance. So you have gamma, which is given as follows. It's p, the set of p such that dp1 of h0, which is equal to p1, is equal to 0. So the resonant line, it's some condition on h0, and more qualitatively speaking, it's when one of the angular components does not move. So let me denote it by gamma 1. And if you look at the ball of actions, then this is just a vertical line, gamma 1. And usually when you do diffusion, you want to try to stick to a resonant line, and you want to diffuse. And if you get off all the technicalities, then what is done in BKZ paper, it says that there exists a number which you could compute, and it depends on the perturbation, H1. And this number tells you how many holes are there. I'll draw you probably 2 holes. And when you look at the holes and what you need to do, you need to remove some neighborhoods. I'll probably say a bit more what are the holes. So what I want to do, I want to puncture K holes, and I want to take epsilon to the 1/6 neighborhood of each. Then it turns out that this picture in some sense survives. The only problem, it gets highly distorted. So basically what you get what we call crumpled cylinder. So what is a crumpled cylinder? Let me use again a blue color. Crumpled cylinder is something which you see in IKEA when you want to buy a lamp. So it's a cylinder which if you stretch it like this, it's going to be a normal cylinder, but they have lamps which you squash it backward. And if you look at the angle here of the leaves of your cylinder, then the angle is going to be square root of epsilon. So now I guess you could train your imagination. It is quite singular in the limit, but for any positive epsilon, you could still construct these cylinders. So you have a vertical component. Okay, so I could write a formula if you like. So d theta 2 di dp1 is of order 1/square root of epsilon. So is this? So there is a variable q here on this picture. When you say that my cylinder is a little bit distorted, you could view q as a function of the other two. Okay. So if you start to view q as a function of the other two, then it behaves wildly, and you need to work out quite a number of estimates in order to control this object. So let's see. So I probably won't have time to say how these cylinders are constructed. So the first key idea is that you need to use theory of normal forms, because if you don't do normal forms, then you will not be able to see such a clear picture. But after you do a theory of normal forms, you do Conley isolating block. So these cylinders are constructed as a fixed point of a certain operator, certain map in the space of graphs. And it's some abstract fixed point, and I don't know, probably Ken next time will tell you about crumpled cylinders. So they're constructed using some abstract fixed point theorem, and we know that they exist, and we know that they have very bad properties, but luckily we could still control it by getting some lower bounds on regularity of those cylinders. And actually this is one of indications why geometric methods had difficulties in doing not a priori stable systems, because geometric methods assume that you have a nearly integrable structure on a cylinder. But what the calculation which we have done in BKZ show is that it seems that the structure here is far from integrable, and in particular, probably there are no secondary tori. So let's see. It's okay. I thought I'm completely out of time. Okay, then I'll say some words about. No, I want to draw a second picture, and if I still have time, then I'll say some words about Conley isolating block. So, let me tell you the difference between. So this picture is what is often called single resonance. So let me say in naive terms, what is a single resonance. So single resonance means that T dot is 1, theta 2 dot is O capital of 1, and theta 1 dot is of order of epsilon. So what it tells you that when you study motions, there are two fast angles, and there is one slow angle. And this is a picture which is similar to Arnold's example. The two fast angles are in this direction, and the slow one is over there. So you kind of view that this is a distorted picture. From here, your slow angle is the position of a cylinder, and the fast angle, you still have orbits which rotate on your cylinder in some fashion. Now let me tell you what is a double resonance. So since I want to diffuse everywhere, and this is necessary for the second theorem, let me look at the gamma 2, which is given, for example, by dp2 h0 equal to p2 equal to 0, and let me look at the intersection point. So I'll probably redraw the picture. So this is p1 equal to 0. That's p2 equal to 0. And for example, at this point, what you have that theta 1 dot is small, theta 2 dot is small, and t dot is of order of 1, and qualitatively the picture has changed. So you have two slow angles, and you have one fast angle. And what I want to do, I want to take an epsilon dependent neighborhood here. For example, there are a lot of technicalities, but let me take a neighborhood of order square root of epsilon and zoom it in. Then, so this is a neighborhood of the origin of the size c times square root of epsilon. And when I first faced this fact, I was really amazed. This is actually chaos zone. So what does it mean, chaos? You have counter sets, you have symbolic dynamics, you have positive topological entropy, you have horseshoes, you have plenty of chaos here. And my goal is to come in and to come out either in this direction or on that direction. And my goal is to draw an heuristic picture, which we managed to prove, which shows how the things occur. And I slightly oversimplify the picture so that it's possible to swallow. So I take, let me call this one E, and this is E times square root of epsilon. And let me start using colors. So I want to use this. This is my diffusion path. This is how I want to diffuse. This is my second diffusion path. Now, this is my third diffusion path, whose meaning will be more transparent a little later. And this is my fourth diffusion path. So now let's remember what I would like to do. For this particular example, I want to start, for example, somewhere up here. And for example, I want to end somewhere here. So it means that I go along one coordinate axis, come into the chaos zone, and I want to come out on the other coordinate axis. So this is just zoom in of this picture. And so now what I claim, you could still diffuse along normally hyperbolic invariant cylinders. And these cylinders have a kissing property. So let me draw. Maybe I'll do this one with purple. So I was hoping it's going to be in a bigger room. So what is a kissing cylinder? Before I do the kissing cylinder, let me draw you an additional picture. So I want to take a cylinder and I want to take a ball out of a cylinder. Okay, so this will be a basic thing in my construction. Now, what are the kissing cylinders? So this is a orange direction. So everything is in 4-dimensional space, and in 4-dimensional space there is a cylinder. Convexity is wrong way. So that's one picture. That's another one. I really want to have some. This is important for the proof. I really want to have. So that's one normally hyperbolic cylinder. So topologically, it's a 2-dimensional cylinder with the ball taken out. Now, what does it mean? There is a kissing. There is a twin brother of this cylinder. And in 4-dimensional space, these 2-dimensional cylinders have 2-dimensional plane of tangency here. So I'll finish a picture and say some more words. So you have a curve which comes in. You have another curve which comes in. Which goes out. And this one goes out. And again, I want to have a little room on both sides. So that's on both sides. So even though it's a Keller zone, so what I claim is that one could make sense of what does it mean direction of diffusion, and one could translate it in the space of homologies, and one could construct the corresponding cylinders. Now, so far I have drawn the green direction and the purple direction, but I would like to come along the blue direction. So first, what is a kissing property? It's a 2-dimensional plane of tangency. 2-dimensional tangency. Now let me draw you a flower cylinder, and then you'll try to say whether it's a flower which you use for cooking or. So that's the boundary is the same, but now let me draw the blue picture. So you have something which doesn't look that much distorted, but I want to have a cylinder, and you see I have really a lack of space. So when I go down on this cylinder, it becomes like a 2-leaf flower. The reason I'm not drawing multi-leaf flower because my graphical abilities are limited, but you could have a multi-leaf flower. So basically, the picture which you have a curve, and then as you go down, this curve pinches into the figure 8. And now, if use your imagination in order to put this picture on top of that picture. So what you have, I repeat. So what you have 2-dimensional normally hyperbolic cylinders in a 4-dimensional space. And now on heuristic level, I want to convince you that I can jump, for example, from the green cylinder to the purple cylinder. No, no. So again, you have normally hyperbolic invariant cylinder. It means that it has one direction of instability, and it has two dimensions in the neighborhood. Right. So what I'm saying is that there is a two-dimensional plane of tangencies, and there is a direction of, say, unstable direction. So you have three-dimensional stable manifold, and you have a three-dimensional green stable manifold and three-dimensional purple unstable manifold. And I claim that they have to intersect because you have two-dimensional plane of tangency, and one direction is purple and another direction is green. So Keesin property implies that you could jump from one cylinder to another. And what is really fascinating to me, this is a robust picture. If you start twisting your mechanical systems, and this picture will not disappear. And another thing which I want to say is that now it requires more thinking, but what I claim is you could actually able to jump from a blue cylinder to a green cylinder. And this already requires a little bit more thinking, but again, these are two-dimensional cylinders in four-dimensional space. They have three-dimensional invariant manifolds, and what I'm claiming is that with some imagination, you could go from blue cylinder to orange cylinder. Certainly, the proof is much longer story, but I hope you kind of see this picture. If you are if you have a Keesin property, then you can actually jump from one cylinder to another cylinder. Now, suppose you know how to jump from one cylinder to another cylinder, then you could imitate the Arnold's game. So what is the Arnold's game? If you know how to diffuse along a cylinder, you go along the blue cylinder, you come sufficiently close. Using Keesin property, you jump, for example, to green guy. Again, using some technology, you could cross the bed region, and later on, if you want to diffuse in this direction, you jump back again because of the Keesin property, and you go along the corresponding yellow cylinder, or you could diffuse along the corresponding blue cylinder. So the emphasis I want to make is that it is in the title. So it's an Arnold diffusion via normally hyperbolic invariant manifolds. So if you trust that you could diffuse along normally hyperbolic invariant manifolds, then what I'm saying, it's yes, technically it's a lot different, but it's more or less a mechanism which was proposed Arnold and Mather, plus possibility to jump from one cylinder into another.
What was the purpose of removing this
You don't know what happens there. You don't know what happens there. It's a chaos zone. Okay, so I mean, in order to do the proof, you need to use actually ideas from a completely different area of dynamical systems. You need normal forms of saddle points, and in conservative dynamics, normal form of saddle points, they are always resonant, and this resonance is a cause of pain, and we need to use Shilnikov a boundary value problem, a beautiful trick which was proposed by Shilnikov, which allows to control the process even though the corresponding saddle point is resonant. So it's in KZ1 and in a second preprint. And to tell you the truth, there were people who didn't believe that this construction is going to work. So it's again, it's a chaotic zone. If you start close to these cylinders, you don't have much of control what your trajectories do. Are there any questions?
I don't understand your cylinder on the left.
This one?
Yeah,
Right. But no. You see, that's why I put it in white color. That's the same what I do here. Um, so yes, huh? Yes, because you add the boundary. If you don't, yeah, this was a painful part in the proof. If you don't add area underneath separatrix, you are in trouble. Add area underneath separatrix. No. I draw what I draw. Yeah. It's and here it's the same story. You need to add the region here. You see? Well, I would say that if you want to imagine an orbit which goes from top to the bottom, then the orbit does something, and then actually what it does, it jumps under the separatrix, goes along the separatrix, and then goes down. If you don't add the boundary, you're in trouble. What do you mean? Normal hyperbolicity is something which happens in the orthogonal directions. The whole plane kissing, I need to write some formulas. Intuitively, you have a saddle point, and saddle point has one direction stronger than the other. And because one direction stronger than the other, if you imagine any curve, so imagine that you have x goes to x over 2 and y goes to y over 4. Then you see practically any point you choose, the orbit is going to be tangent to this direction. Okay? So you could imagine that more or less any manifold you pick, it's going to be tangent to weak direction. So yeah, because it squashes it in, and that's actually what happens in the proof. No, it's actually saddle. It's not quite. It's a chaos zone. It's completely all the four directions are hyperbolic. So if you draw this picture here, you get tangency to this direction, and if you draw a backward picture here, you get the tangency in that direction. So you have a kissing property because they are tangent to strong stable and strong unstable manifold, because the dynamics squashes it, and they have to be tangent to the directions which dominate, to the directions transversal to those they dominate. Okay, so I have maybe 4 minutes, 3 minutes, 5 minutes. Okay, maybe I'll tell you about the idea of Conley, of how you could construct crumpled cylinders, and this was actually something which opened our eyes. Even though the system looks nearly integrable, actually there is a competition, and I hope I would be able to tell you the competition. So let me tell you about Conley isolating block. So remember, my story is always I want to construct normally hyperbolic cylinders. I want to construct lower dimensional manifolds inside of a higher dimensional space. So here's an abstract result which was proposed by Conley. So what I want to do, I want to write my system in coordinates. So this will be my stable direction. That's going to be my unstable direction, and there is some central direction. And I want to impose some condition on my vector field. So my vector field I want to be unstable, stable, unstable, central. And it's a very abstract general result, which is of huge help. So V, U, U, I form linearization matrix. And when you form linearization matrix, then what you want to do, you want these terms to dominate the story. So imagine for a second that U dot is equal to U, and S dot is equal to, I need to switch this, U and S, and S dot is equal to minus S, and you want to say plus a perturbation. Then what Conley noticed is that there is a very mild condition which guarantees existence of a normally hyperbolic cylinder. The mild condition says that you want your vector field to point outside on unstable directions, and you want to point inside on stable directions. And if you imagine for a second that there is a saddle here, then you say there should be a fixed point. But remember, there is also a central direction. And so let me state isolating block condition. So the isolating block condition says that U times U is positive on the boundary. So it means that on the boundary, on the unstable boundary, you're pushed outside on the green part. And then the another condition is that on the transverse boundary, you are pushed inside. So suppose on the green boundary you are pushed outside, on the red boundary you are pushed inside, then plus a cone condition, which I don't have time to formulate. The conclusion is that this vector field, which satisfies condition one number bigger than the other and two numbers are positive, the conclusion is that this vector field has normally hyperbolic invariant manifold. And I want to emphasize this is in many dimensions. So this could be 50-dimensional, this could be 100-dimensional, this could be 25-dimensional. But the dimension of a cylinder is the same as the dimension of central. Yes. So it's an abstract fixed point theorem, and in order to prove it, you need to do graph transform. And we, at least the way I learned it, I read a very nice paper by McGehee. There are other sources, but the way crumpled cylinders are constructed through some abstract fixed point theorem. So you don't know what your vector field does inside, except of stretching in these directions and contracting in these directions. And if you have this information, then it's enough to establish existence of this normally hyperbolic cylinder. Then you go to the estimates and you see that it's actually crumpled. So if you don't have a fixed point argument, it's not clear how would you catch it. Maybe this was the reason it was hard to catch these cylinders. Dominating, exactly. The cone condition says that this term dominates the rest, and negative of this term dominates the rest. And again, these are numbers which you compare, and if you have it, then so. No. No. A is bigger than the sum of CD.
If other were zero, then it would be clear case, and if they are small compared with diagonal.
But small could be 1/2 of the rest.
No, small, I mean, no, not much.
It's important that it's not perturbative. It's order of 1. This could be 0.1, 0.1, 0.1.
But you can have several of the cylinders.
If you have a cone condition, then you don't. It's unique. If you have a cone condition. With a cone condition, it's unique. The unstable if you imagine that you have unstable manifold this way and the stable manifold that way, it lives in the intersection. Yeah, yeah, yeah. But it's important that this is order of 1 perturbation. This could, if all these entries are 1/10 of these entries, then you could do the fixed point. So right. So the dimension for our problem, this is 2. The central is 2-dimensional, and unstable is 1. Stable is 1 for theorem 2. But for theorem 1, this is n-1 dimensional and n-1 dimensional. So theorem 1 was in any dimension. And in any dimension, this is arbitrary dimensional, and this is the same dimension. So it's essential that this is not 2-dimensional argument. This is, so for theorem 1, this is Rn-1, and this is Rn-1. Well, imagine that you start with a curve like this, and you start iterating it. So it's stretched, but the point is that it starts at the left and ends at the right, and the image starts at the left and ends at the right. Okay, and this property is preserved. You are pushed outside, but you are stretched. You cannot break it. It's like you imagine a surface. You keep iterating it, and then you could show that in a certain Banach space, there is a fixed point because it's a constructing operator. So there is a contracting fixed point, contracting unstable. There is a manifold which attracts everything, and it will be unstable manifold. Now you take something in the opposite direction and you start iterating backwards. So the point is that if you take something which is attached to the boundary, the boundary is only pushed to the other side, so the projection is still going to be everything.
So Conley's theory says there's some invariant set inside, but then you have the smallest condition, so I think you can show that then that gives you the uniqueness. So you don't actually need a contraction mapping principle. I think it tells there is some there this invariant the invariant set inside. But on the invariant set, then presumably you could use this hypothesis and show that have to be points.
Right.
What is your
Huh? This guy dominates all the rest, and inverse of this guy dominates all the rest.
But you don't require that one contracts.
No, this is negative. Okay, so VUU is at least alpha times the identity matrix. So this is symmetric. And VSS is at least minus alpha times the identity matrix. Yeah. So yeah, so it's kind of the alpha is here. You need to have some strength, right? If you don't have strength, then you cannot do it. I mean, you cannot hope to do it. Yeah.
Just to make sure, going back to the statement of the theorem, the perturbation H1 can be C infinity smooth.
Right.
And it would still be like the statement would be for C infinity generic on your only CR activates. If you want it to be generic, it has to be CR.
I don't think we claim C infinity, but I think it is true. Do you think it is true? I'm
For a fixed star. But certainly if you're just looking for one, you can make it C infinity.
yes. These guys are persistent. Once you construct them, you smooth it out, and everything is C infinity. These are the structures which do not disappear even under C2 perturbations. So these are the structures which will be there. So C infinity, I guess, perturbing barrier to keep generic. This is where we cannot do it infinity. I mean, C infinity, I don't know. But the cylinders, no. The question is that can you do C infinity generic? And we are not sure that you could do C infinity generic because of genericity of barriers. But you need